Good morning, students. So myself, Vijay Shankar from Electronics and Communication Engineering Department, Chevron Engineering College. So today we are going to discuss about the examples, Fourier transform examples. Okay. The first example, in the last class, yesterday's class, we learned the different properties of the Fourier transformation. And one example also, my dear students, that is the same example, Fourier transform of the decaying exponential, Fourier transform of the decaying exponential. Okay. See here they're showing that a decaying exponentially, the characteristics a truncated decaying exponential pulse. So at this place there is e power minus at. E power minus at means that t is equal to 1 by a e power minus 1. E power minus 1 is a 0.3678. And at the 0, e power minus at, the t is equal to 0. E power 0 is the 1, my dear students. So it starts at the 1 and slowly it is decreases, and at 1 by a the value is a 0.3678 and goes on decreases and equal to the 0 at the infinite. And there is no any function in the negative real axis at the negative values of the t. For that case, the given signal x of t is multiplied with the step function. Why? The step function having its magnitude is 1, mu of t is a step function, magnitude is 1 from 0 to infinite of the t values. The negative real axis, all the values is a 0. So multiplying these two functions as a signal given, the x of t is equal to e power of at minus at mu of t. Because the Fourier transformation is not use it for analysis of the periodic signals, for the aperiodic signals. The mu of t is equal to t is greater than or equal to 1, not the 1, t is greater than or equal to 0. The mu of t is equal to 1 and 0 for the t is less than 0, my dear students. T is less than 0. So there is no any value. All the negative values of the t, the mu of t is equal to 0. So the given decaying exponentially exponential pulse x of t is equal to e power minus at mu of t at the t is greater than or equal to 0. Here that mu of t is equal to 1. Okay. So by the definition of the Fourier transformation, we also know that x of f is equal to integral minus infinite to infinite x of t e power minus g 2 pi f into t dt. Okay. The x of omega is also the minus infinite to infinite x of t e power minus j omega t dt. Is for angular frequency and for the normal frequency. The given the signal minus infinite to infinite, x of t is e power minus at mu of t, e power minus at mu of t, and e power minus j omega t dt. Okay. The mu of t, the value is 1 for t is greater than or equal to 0, my dear students. Now I am changing the values integral with respect to the t. With respect to the t means the limitations is also the t values minus infinite to infinite. The mu of t is not all the values is a 1. Only from 0 to infinite, e power minus 80, and this value is 1 in the range of 0 to infinite. See here, the 0 to infinite. E power minus j omega t dt. Okay. Now bases are the same. You can add the powers. You can add the powers here. That is equal to integral 0 to infinite e power minus, you can take as a common, a plus j omega into t dt. Okay, my dear students. We know the integral of e power x or the e power minus x. E power x is there, e power x by 1 with respect to the x is there. And here with respect to the t, whatever the coefficient we'll have, that will get in the denominator. So after applying the integral, e power minus of a plus j omega into t whole divided by minus a plus j omega with the upper limit infinite and the lower limit is 0 after applying the integral here. Okay, so denominator, now the e power minus a plus j omega into t is e power minus infinite. Infinite to anything is infinite only, my students. Minus the lower limit is e power minus 0 because the t value is 0, anything into 0 is 0 by minus of a plus j omega. Okay, I already told the e power infinite always 0 minus e power 0 is always 1 minus a plus j omega. So numerator is a minus is there and denominator having the minus, both are get cancelled. Finally you'll get 1 by a plus j omega. So x of omega is equal to, we got x of omega is equal to 1 by a plus j omega. The Fourier transformation of e power minus at mu of t. Okay, my dear students. But here they are showing in the x of f in the normal frequency. What is a Fourier transformation? Got 1 by a plus j. Substitute the omega as a 2 pi f. Both are the same. X of f is equal to 1 by a plus j 2 pi f. With the decaying exponential pulse e power minus at mu of t. Okay. And to find the magnitude and the phase spectrum, of this function, I'm taking the 1 by a plus j omega actually as in terms of angular frequency, rationalized a minus j omega whole divided by a minus j omega. Okay, my dear students. So numerator having the a minus j omega and denominator is x of omega, my dear students. X of omega is equal to, we got 1 by a plus j omega. Rationalized with a minus j omega by a minus j omega and denominator c a square minus b square, a plus b into a minus b. What is the j square is equal to minus 1. A minus j omega whole divided by a square j square is a minus 1 and the minus is already there. A square plus omega square. X of omega is equal to. In this, which one is a real part? A by a square plus omega square is a real part. And imaginary part is omega by a square plus omega square. As of x of omega. From this, the magnitude of x of omega is equal to, magnitude means under root of a by a square plus omega square whole square plus and b square. What is a b square? Omega by a square plus omega square whole square. That is a magnitude. Magnitude of x of omega. And phase, because it is a minus b, a x minus jy. So the angle of x of omega, the phase angle of x of omega is equal to minus tan inverse imaginary function here, the omega. Denominator is the same for the real term also, omega by a. Why I am using the minus? Because it is the fourth quadrant, my dear students. So x is a positive and y is a negative, means it's the fourth quadrant. The phase angle is minus tan inverse y by x. It's the first quadrant plus tan inverse y by x. And in the second and the third quadrant, the phase angle is 1. In one quadrant, you have to add 180 degrees. In another quadrant, you have to subtract 180 degrees. Okay. Now we got the magnitude and the phase. By using the omega is equal to 0, omega is equal to infinite. And here also omega is equal to 0, omega is equal to infinite, and so on. Take the values. Let us see. The same thing here, the x of f is equal to a plus j omega. I take the j omega angular frequency. After finding out the real part, a by a square plus omega square. This same thing, a by a square plus omega square is the real part. Imaginary part is minus omega by a square plus omega square. Minus omega is nothing but 2 pi f. Magnitude you can see a square by a square plus omega square whole square. Omega nothing but 2 pi f here. 2 pi f. Now here minus 2 pi f. Minus whole square is always a positive value only. Omega becomes 2 pi f whole square and denominator is a square plus omega square. And simplify this equation as numerator having the a square plus omega square and denominator having a square plus omega square whole square. So magnitude of x of omega is equal to, after simplifying, 1 by, or not that, 1 by under root of a square plus omega square whole divided by a square plus omega square whole square. So this is a one term and square get cancelled. It becomes of 1 by under root of a square plus omega square. Using these values, the omega values, you can plot the magnitude and the phase. What is a omega? Let us see. Omega is equal to 0 for the magnitude spectrum, my dear students. For the magnitude spectrum, omega is equal to 0. What is the value here? X of omega is equal to, we have 1 by under root of a square plus omega square. That is equal to 1 by omega square is a 0, a square plus 0. So under root and square get cancelled. It is a 1 by a. 1 by A. A is equal to 1, let us say. A is equal to 1. At 0, the value is a 1. And at omega is equal to plus infinite, if I am taking x of omega is equal to 1 by under root of a square plus infinite square. Means infinite plus anything is infinite, 1 by infinite is a 0. What is a 1 by infinite, my dear students? It's a 0. Slowly it is decreases and finally at the infinite it becomes a 0 value as a plus infinite. Similarly, in the minus infinite, x of omega is equal to 1 by under root of a square plus minus of omega square. Omega nothing but here I have taken the minus infinite. Always again it is also the same of under root of a square plus infinite square only, my dear students. It is also the 0 because 1 by infinite is a 0. So for the minus infinite also it goes to the 0 one. So slowly it is a decreases and at minus infinite it becomes a 0, and here also it slowly decreases from the value of 1 by a or 1. Slowly it decreases and meet the 0 at infinite. The magnitude spectrum. Magnitude spectrum, my dear students. Okay. When coming to the phase spectrum, what is a phase? We got tan inverse minus tan inverse y by x. What is a y? Omega by a. Omega by a. The phase angle, magnitude angle of x of omega is equal. Here when I am taking the omega is equal to 0, what happens of angle? Angle x of omega is equal to minus tan inverse omega, nothing but 0 by a, that is equal to minus 0. Minus 0 plus 0, whatever it is, a 0 only here. The angle is 0 at omega is equal to 0. Here it is a f, because they are taking that in terms of f value. I am taking it in terms of the omega, angular frequency. And coming to the omega is equal to infinite, what is an angle? For the phase spectrum, my dear students. These are the phase spectrum. Okay. Minus tan inverse omega is a infinite by a. That is equal to minus tan inverse infinite. What is a minus tan inverse infinite? Minus tan inverse infinite is a pi by 2. It is a minus pi by 2. So for infinite, see here is there is a f is equal to the omega is equal to infinite value. What is an angle here? Minus pi by 2. Okay. Similarly, at omega is equal to minus infinite, if I am taken, the x of omega is equal to minus tan inverse minus infinite by a. You know the tan inverse of minus x is a minus tan inverse x. So minus into minus is a plus. Tan inverse infinite. It becomes a plus pi by 2 in the 90 degrees. So for minus infinite, what is an angle here? Pi by 2. So phase 0 here for infinite value, saying that here for this infinite value, that's a minus pi by 2, and the minus infinite, the value is pi by 2. So it varies in between of the pi by 2 and the minus pi by 2. Okay, my dear students. For the given signal x of t is equal to e power minus at mu of t, the Fourier transformation is x of omega is equal to 1 by a plus j omega, and its magnitude spectrum and is a phase spectrum for the values of omega is equal to 0, omega is equal to infinite, and omega is equal to minus infinite. All right. It's a very important matter, students. Hope everybody understood this one. Okay. So coming to the next one, next example, my dear students. So obtain the Fourier transform of rectangular pulse. We given the rectangular pulse here. Rectangular pulse of duration t. Why it is a t? Minus t by 2 the 0 is a half, and 0 to t by 2 is a half. Total is a time period is a t. And its amplitude a, as shown in this figure. But to find out the Fourier transformation of this rectangular pulse. What is given here? The rectangle of t with the time period. The time period is given the t by t. A is the magnitude in the range of minus t by 2 the less than the t by 2. Means t is greater than minus t by 2, and this t is less than the capital T by 2. Okay, why I wrote here the t? See, in the scaling factor, we already discussed about x of t having t is the time period, x a of t having the t by a is the period, my dear students. Okay, so rect of t by t. So the given x of t is a into y. I say take a is amplitude, and the rect of t by t. The rect means a rectangular pulse. The rectangular pulse. To see the given signal x of t, have to find out the Fourier transformation. Here they explain with the normal frequency. I will explain the angular frequency, my dear students. X of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. I want the definition of the Fourier transformation. The given signal x of t, its Fourier transformation is x of omega. In this example, they're asking that how to obtain the Fourier transform of rectangular pulse minus infinite to infinite. What is x of t? A into the rect of t by the t e power minus j omega t dt. Given signal. But this given signal is having the amplitude is a, having its amplitude is a, in between of minus t by 2 the t by 2. The remaining all the values is a 0, my dear students. So change the limitations minus t by 2 the t by 2. And keep that rectangle is a, only the magnitude is a into e power minus j omega t dt. And this rectangular pulse is a 1. But a is a constant. Apply the integration of e power minus j omega t. You get the e power minus j omega t by minus j omega with the limitations t by 2 and minus t by 2. T by 2 and minus t by 2. Substitute the upper limit a into e power minus j omega. Upper limit is a t by 2, my dear students, minus e power, when I am substituting the lower limit is a minus value, minus and minus becomes a plus j omega t by 2 whole divided by, here already the minus j omega is there, j omega. Okay, same thing here, a by pi f they are given. Pi f means 2 pi f here, the 2 is there and 2 pi f omega only, e power j pi f into t. Pi f into t means omega is a 2 pi f, 2 to get cancelled, pi f into t only you have. Okay, now here the minus is there and multiply the minus the numerator, it becomes of x of omega is equal to a into, I'm multiplying this minus with the numerator values. So e power minus e power j omega t by 2 becomes of a plus j omega t by 2 as the plus minus e power minus j omega t by 2 whole divided by is a j omega. Now the x of omega is equal to, I am multiplying and divide with the 2, my dear students, 2a by omega, 2a by omega whole multiplied with what is the numerator, e power j omega t by 2 minus e power minus j omega t by 2. Okay, whole divided by, I multiply the numerator as a 2, here you can multiply the denominator also, 2j value. Now observe here, it is in the form of e power jx minus e power minus jx by 2j. Well, that is a sin x value. Okay, according to the Euler rule, 2a by omega e power jx minus e power minus jx by 2j. What is the x here? Omega t by 2. So sin x, sin omega t by 2, sin omega t by 2, x of omega is equal to. Okay, my dear students, not only we have got here, x of f is equal to a by pi f. Why it is a pi f? Omega is equal to 2 pi f, my dear students. 2 to get cancelled, a by pi f sine. Here also the omega is 2 pi f into t. 2 to get cancelled, a sine pi f t. X of f is equal to. X of f is equal to. These two are the same, my dear students. Okay. It is in the angular frequency. Now it is in the normal frequency. But I am changing this as a into t, the sine pi f t, the sinc function. So x of omega is equal to 2a by omega sine omega t by 2 whole divided by sine omega t by 2, you can take it as the omega t by 2 in the denominator. Already the omega is there, no need of taking this t. So I'm taking here, this omega is here, omega. I'm multiplying the t by 2 here. And now you take the value is a t by 2. Okay. Multiplying and the dividing with the t by 2. Numerator is a t by 2 and denominator is also t by 2. And if the t get cancelled, So x of omega is equal to, it becomes of a into t sine theta by theta. We already know sine theta by theta. Sinc function, see here. Sine theta by theta, or the sine x by x is a sinc x. The omega t by t and omega t by t, it becomes of a sinc ft, or 2 pi f means the 2 will get cancelled, and we have pi t and the pi t, sine pi x by the pi x. So sinc x. Okay, sinc x. Pi we can change this as a sinc. We'll get f the t. Okay, my dear students, it becomes of 2 pi f here. 2 pi f by the t. 2 to get cancelled, pi f t here. And the denominator also, 2 pi f into t means pi f t. Is a sine. You know the sine pi x by with pi x means sinc x. So what is the coefficient of pi here, the x, and here the x, and here it is ft. So x of omega is equal to at into sinc ft. Even if it is x of f also we got the same. At into sinc ft. It is also very important, my dear students. The Fourier transformation of the rectangular pulse of the duration t and the amplitude a is shown in the figure. The Fourier transformation of this rectangular pulse is x of omega is equal to at sinc ft. Understood? Now we go for draw the rectangular pulse and the phase amplitude spectrum and the phase spectrum. Amplitude spectrum is nothing but the magnitude only, my dear students. What we got here, x of omega or f. X of omega or the x of f is equal to at sinc f into t. Is it right? See here. X of f or the x of omega, at sinc f into t. The amplitude spectrum and the phase spectrum. In the phase spectrum below, the negative values of amplitude x of m are made positive by phase shift of plus or minus 180 degrees in the phase spectrum. Plus or minus 180 degrees in the phase spectrum. See the amplitude, if I am taking the omega is equal to or f is equal, because it is in terms of f only, my dear students. Let f is equal to 0. F is equal to 0 means x of 0 is equal to at sinc 0. Sinc 0 means the values are maximum peak at f is equal to 0. See the f is equal to 0 value, 80. Sinc is nothing but the sine pi into x or pi ft by the pi ft. Sine pi the pi, the t wave f is equal to 0 value, the sine 0 by 0 is undefined. Sine 0 is a 0 and the 0. Okay, my dear students, but how to find in another way the x of 0 when the f is equal to 0 function, we'll get the maximum peak. Maximum peak at 80. The amplitude is 80. Slowly it is decreases and it becomes a 0 when f is equal to 1 by t, my dear students. For every term of 1 by t, 2 by t, 3 by t, and so on, it goes to the zeros. And slowly it is decreasing its amplitude also. When f is equal to 1 by t, the x of f becomes a into t, sinc function, the sinc ft. What is the f here? 1 by t. 1 by t into t. T get cancelled. The sinc 1. The sinc 1 value is a 0. Why you are saying, sir, this is a 0 and this one is a sinc f of t is the sine 0 by 0. The value is L'Hospital rule. Here you can apply the L'Hospital rule. L'Hospital rule. What is the L'Hospital rule? Means take the derivative of numerator and the denominator. Take the derivative of numerator and the denominator. When f is equal to 0, it is a sine 0 by 0. Because f is equal to 0 here, my dear students. Sine sinc theta is equal to sine theta by theta. Sinc pi theta, my dear students. Sinc theta is equal to sinc pi sine pi theta into pi theta. Okay, the theta value is a sinc here, the f of t. So sine pi theta and pi theta, it becomes of sine. Sine is a cos, my dear students. Cos pi theta into pi whole divided by, for pi theta, with respect to, we are applying the theta one, the derivative. L'Hospital rule means take the numerator and apply the derivative with respect to the theta. That is a cos theta, cos pi theta, and the theta coefficient is a pi. And the denominator also, you can apply the derivative, my dear students. Pi theta is a pi only, theta is a 1. So pi get cancelled and this becomes of cos theta. What is the theta we are taking here? The 0. What is the cos theta? 1. Follow my dear student, 1. So what is the multiplication factor here? 80. So we got at f is equal to 0. Directly we can substitute in this equation of x of 0. It becomes is a sine 0 by 0. It is undefined condition. So using the L'Hospital rule, sine pi f t. Here the theta is nothing but, my dear students. Don't confuse, the theta is ft only. Theta is the ft. Sinc ft. Sinc ft means here also the ft, pi ft. Okay. And sinc sine ft with respect to, we are applying the f. So pi t, sine ft by the pi ft. For the numerator, apply the derivative with respect to the f. With respect to the f, my dear students. With respect to the f. It becomes of sine pi ft, we'll get cos pi ft into pi t. Okay, my dear students. And here also, the denominator becomes of pi ft. With respect to f, we are applying the derivative. What is the constant here? The pi t. So pi t get cancelled, cos pi ft. So when f is equal to 0, it becomes of cos 0. Cos 0 is a 1. And it is multiplied with the 80. and here also the 80, and here also the 80, and 1 into 80. So at f is equal to 0, the value is 80. See here, and f is equal to 0, the maximum value is 80. Don't substitute directly, my dear students. If it is substitute directly means that value becomes of undefined, 0 by 0. We can't define that one. So by using L-Hospital rule, you can follow the sinc function is always at 0, it's a maximum peak and goes on increasing or the decreasing of the f values for every time period of 1 by t, 1 by t, 1 by t, it goes to the zeros. So let us see the 1 by t. At f is equal to 0, the x of f is equal to at sinc ft becomes the value is 80 only, 80 into 1. Now I'm taking the f is equal to 1 by t, my dear students, 1 by t. What becomes x of f is equal to a into t, sinc ft means sine pi ft by pi ft, my dear students. What is the f here? 1 by t. So is equal to at sine pi f 1 by t into t whole divided by pi f, nothing but 1 by t into t. So t get cancelled, here also the t get cancelled, becomes of at sine pi by pi. Now here also you can use L'Hospital rule. At, what is the sine or sine derivative? Cos pi. And pi is equal to 1, my dear students. Sine theta by theta. Sine theta is a cos theta and the 1. Okay. So directly you can substitute here, my dear students. Now if I am taking it is pi ft. Here it is a cos pi, now it becomes of minus 1. Minus 1 is a minus 80. Minus 80 means it is not in the here, it is a, you get at the minus. It is also not correct. Without substituting the value, x of ft is a sine pi ft by pi ft. At is equal to sine eft into theta. So you're applying that, it is a cos eft into pi eft, my dear students. Whole divided by the same thing, you'll get pi into pi ft, having only the ft here. Ft. So ft get cancelled. And when the f is equal to 1 by t, at into cos pi only, cos pi x of f, 80 into cos pi. And 2 pi, 2t is also, you can take it as a 2t, f is equal to 2t, the cos 2 pi, cos pi, 180 degrees. And 2 pi, the cos 2 pi is also the value the same, and the 3 pi is also the same. It is decreasing. Let us see. When we are going, my dear students, when we are going for the hospital rule means if any undefined state we got, because when I sync ft sine pi to the sine pi t means sine 0 by 0, it is a 0 by 0 undefined symbol, then we are going for the L-Hospital rule at the f is equal to 0. And here, no need of going for the L-Hospital rule. No need of going to the L-Hospital rule, my dear students. Understood? Directly when I'm taking the 1 by t, the values becomes of 0 with the lowest amplitude, and at the tt, it goes again the 0 and decreasing its amplitude. For the same value, for the negative values also minus pi by 1 by t, minus 2 by t, and minus 3 by t. But these values, when we are substituting the f is equal to, don't use the L-Hospital rule here. Why it is not getting it is undefined states. When f is equal to 0 only, we are getting the undefined state. Then we are going for the L-Hospital rule. And we are going to the L-Hospital rule. For the remaining, don't go for the L-Hospital. And directly you can find out the values. When 1 by t, and f is equal to 1 by t, and f is equal to 2 by t, and f is equal to 3 by t. Sine functions only. Directly you can take is the sine functions. Don't go for the L-Hospital rule, my dear students. F is equal to 1 by t. What is the x of f? X of f is equal to at. Sin function means sine pi ft by sine pi ft. Okay, that is equal to at sine pi by pi only. Ft and ft. So f is equal to 1 by dt get cancelled, 1 by dt get cancelled, becomes a 0. Following, my dear students, becomes the 0. And similarly, f is equal to 1 by 2t also. 1 by 2t also, the x of f is equal to at sine pi ft whole divided by sine pi eft. What is the f here? 1 by 2. F is equal to at sine pi into pi by 2t and 2t. T here. Pi into 1 by 2t into t. Tt get cancelled is pi by 2, and here the pi by 2. Sine pi by 2 the pi by 2. Angle. Again it is a sin function, is a repeated. Sine pi by the pi. Sine pi by 2 the pi by 2. So on the values. So all it is a decreasing the 0 values. The negative amplitudes of this pulse is made positive by the phase shift of 180 degrees here. For this. Okay, the phase shift of 180 degrees to make the magnitude f is a positive. Magnitude of x of f is a positive. Following, my dear students, repeated, it is a goes on decreasing. The similar way you can take it is a phase spectrum. For the phase spectrum, what is the phase here? The AT and the sync FT. In that, they're explaining that it is a the negative values of amplitude, magnitude of x of f are made positive by phase shift of plus or minus 180 degrees, plus or minus 180 degrees in the phase spectrum. So it becomes of a positive cycle and it is those zeros. And again, the phase shift is for 180 degrees to make a positive magnitude of x of f. And again, it is a 0, 1, and the positive value again goes to the 0. And here also, you see, goes on decreasing value. The ideal condition is a 0. And for the positive value, goes to the negative values here. And again, the 0 and becomes of positive, negative values. So plus 180 degrees and minus 180 degrees is repeated. In the previous example, it is a minus 180, minus pi by 2 to the pi by 2. It varies from minus pi by 2 to the pi by 2. And here the amplitude spectrum and the phase spectrum of a rectangular pulse. And we have positive cycles. The negative amplitude of the pulse is made positive by phase shift of 180 degrees. So 180 degrees phase shift means, you see here, it is a 90 degrees phase shift only. 90 degrees phase shift. So totally, if the 180 degrees phase shift means, when it shows here it is a 0 value, 90 degrees phase shift, my dear students. And move towards, it is a 180 degrees phase shift. 180 degrees phase shift. So 90 degrees only. And it becomes, it is a 180 degrees phase shift. So totally 180 plus 180 and 180, 180, 180 degrees. The positive half cycle and negative half cycle, and positive goes to negative pulses. Okay. The Fourier transform pair of sinc and the rectangular pulse is a rect of t by t. The Fourier transformation is at sinc ft. Sinc means you have to remember, only you have to remember, my dear students, sinc at the 0 the maximum value, and every time period, for every time period 1 by t, 2 by t, and the 3 by t goes to the 0 value. Goes to 0 value, my dear students. Next, Fourier transform of a periodic function. Fourier transformation of a periodic function. So until now we are saying that is a period of our Fourier transformation is also can non-periodic signals. Okay, analyzing the non-periodic signals. And Fourier transformation of a periodic function. Okay. So Fourier series is always used for analysis of the periodic functions only. And Fourier transformation not only for the periodic and also the non-periodic functions. Coming to the periodic function here, the Fourier transform is a limiting case of Fourier series if the period of periodic function becomes a period of a periodic function becomes infinity. Then the spectrum given by the Fourier series, then the spectrum given by the Fourier series will be same as that of the Fourier transform. If the period of a periodic function, my dear students, listen carefully here. If the period of a periodic function becomes infinite, in this case, the spectrum given by the Fourier series, will be same as the Fourier transformation when the period is a infinite. If the period of a periodic function is infinite, the spectrum of the Fourier series given by the Fourier series and will be the same as that of the Fourier transform. That it is a continuous. The reverse way is also possible, that the Fourier series is first a limiting case of Fourier transform. Thus, Fourier transform of both periodic and non-periodic signals can be obtained. Listen carefully. Fourier series is only obtained by the periodic functions only. But here the Fourier transform of both periodic and the non-periodic signals can be obtained. This is extremely useful in signal analysis. This is extremely used in the signal analysis. We know that Fourier transform of a periodic function extending from minus infinite to infinite cannot be obtained by using direct principles studied. This is because such function is not absolutely integrable. Absolutely integrable. Why? They are saying there is a discrete conditions, finite discontinuities, finite peak, single valued property, and absolutely integrable. Absolutely integrable. Otherwise, we are saying that these conditions are necessary. These conditions are sufficient but not necessary. Okay, for the Fourier transformation. See here, for periodic function, the last discrete condition saying that absolutely integrable. Absolutely integrable means less than the infinite. But here, the integral minus infinite to infinite, the magnitude of x of t dt is infinity, is equal to infinity. It is not less than the infinite. For a periodic functions, Fourier transform can be obtained over integral over the interval of minus t by to the t by 2, one time period, nothing but one full cycle. Such periodic function can be expressed by the Fourier series. The Fourier transform of the function is given by the summing Fourier transform of individual components of a Fourier series. Okay, the exponential Fourier series of a periodic function of period t can be expressed as. So we know that Fourier series function is 1 by t, the integral t to t plus t naught x of t e power minus j k omega naught t. Omega is nothing but 2 pi by t naught is 2 pi f naught. Is the equation for the exponential Fourier series, my dear students. 1 by t, the integral t to t plus t x of t e power minus j omega t dt. Okay, where here the xp of t is a periodic signal with a period of t naught. X of t is a non-periodic signal. When I am taking this specific x of p, Cn is equal to p is a periodic suffix, and there is no any suffix here. The x of t is a non-periodic signal. Xp of t, when it is indicated in the Fourier transformation, that is a periodic signal with a period t naught. The Fourier transformation, if they use any xp suffix, x of t indicates a non-periodic signals. Following, my dear students. So since 1 by t naught is equal to f naught, the above equation becomes c is equal to, or Cn is equal to, exponentially Fourier series. Cn is equal to 1 by t naught integral t 2 t plus t naught xp of t e power minus j 2 pi f naught into t dt. 2 pi f naught is the omega naught only, my students. And the above equation xp of t is a synthesis equation. The synthesis equation we can written as a sum of one. Sum of n is equal to minus infinite to infinite Cn e power j 2 pi f naught into t. Don't confuse here. We already learned in another way, my dear students. X of t is equal to the sum of k equal to minus infinite to infinite x of k e power j k omega into omega naught into t. Here they wrote x of k as a cn. So cn, n is a suffix, my dear students. N is equal to minus infinite to infinite. Since they are assuming the Cn is equal to xn, x of k, not xn, x of k. So I'm changing the k values as n is Cn, e power j k, omega naught is a 2 pi f naught into t, x of t is equal. Since it is a periodic signal, it is x of t. The same thing. Sum of n is equal to minus infinite to infinite Cn e power j k. K is equal to here the 2 pi f naught n you are taking. So because it is a n, no need to write. This is not the k, my dear students. It is a n. Changing the n. So e power j 2 pi f naught into n into t. Similarly, the Fourier series expression, the x of k as Cn is equal to 1 by t, the integral t to t plus t. Here it is x of t. X of t is nothing but the periodic function xp of t, e power minus jk. K becomes now it is a n, k, jk, omega naught. Omega naught is becomes of 2 pi f naught into t with respect to the t, dt. The same equation, Cn is equal to 1 by t naught they are taking. T to t plus t naught, xp of t e power minus j 2 pi f naught into n into dt. Here we can have written xp of t to indicate that it is periodic with the period of t naught. By taking the Fourier transformation on both sides, x of t in above equation, the Fourier transformation of this function, integral minus infinite to infinite, the Fourier transformation of the sum of that function, the Fourier transformation of the x of t, integral minus infinite to infinite, is total as a signal. That signal is the sum of n is equal to minus infinite to infinite Cn e power j 2 pi n f naught into dt is a total signal, my dear students, as f x of t. The Fourier transformation definition is saying that the integral minus infinite to infinite x of t e power minus j omega t dt. What is the x of t? I'm assuming the total function. X of t is equal to sum of n is equal to minus infinite to infinite Cn e power j 2 pi n f naught into t. Substitute here. Okay. So take the n value, sum of n is equal to minus infinite to infinite Cn, integral minus infinite to infinite. Here the two exponentials with the base same. Add the powers j 2 pi f minus n into f naught into t dt. And sum of n is equal to minus infinite to infinite Cn. The integral of exponential functions you can written as a delta function. Delta of f minus n into f naught. So suppose here the f minus f naught. Whenever if it is the minus infinite to infinite, my dear students. So e power integral minus infinite to infinite e power j x j 2 pi into, let us take it as a x into t, not the x into t. e power j 2 pi, the minus, here the f minus n into f naught into t dt. You can apply the integration for this one, e power j x, x means the t here. The coefficient is a minus j 2 pi f minus n into f naught. And you'll get in the denominator. After that, taking the upper limit is e power minus infinite is a 0, minus e power minus infinite is again it is a 0. The total integral becomes a 0 value. Okay, whenever if it is a integral minus infinite to infinity e power jx into dt becomes of delta of this function. Delta of the function. The cos actually it is a becomes of e power jx is a cos x minus j sin x. Cos x minus j sin x. So it is represented as a delta function. Sum of n is equal to minus infinite to infinite cn integral minus infinite to infinite this total including the dt also. Delta of f minus n into f naught. Understood, my dear students? Thus, the Fourier transform of a periodic signal x of t is x of f is equal to sum of n is equal to minus infinite to infinite cn into delta of f minus n into f naught. This is a very, very important, my dear students. So you have to remember this equation for the next chapter, the sampling, it is very important. X of f is equal to the sum of n is equal to minus infinite to infinite cn delta of f minus n into f naught. The delta function you can match. Why it is, suppose delta f is equal to 1 for f is equal to 0. If delta of f minus 1 is equal to 1 for f is equal to 1. Delta of f minus 2 is equal to 1 for f is equal to 2. So, for f is equal to 0, the value is 1 here. And similarly, for f is equal to 1, the value is 1 here. And f is equal to 2, the value is 1 here. And similarly, for f is equal to minus 1, the value is here. F is equal to minus 2, the value is here. Now combining all the functions means the sum of delta of f plus delta of f minus 1 plus delta of f minus 2 plus and remaining here also plus delta of n plus 1 delta of n plus 2 so on. So after adding this function, it becomes of 1 here, 1 and 1 and 1. All the ones only. Is the sum of n is equal to minus infinite to infinite delta of f minus n into f naught. The converting of continuous time function to the discrete by sampling. By sampling, we are converting analog function to the discrete. And discrete function we converted to the digital by quantization. And the continuous time function to the convert to the digital function after sampling and the quantization. Continuous time function becomes digital signal. Understood, my dear students? It's very, very important in the sampling. Sum of n is equal to minus infinite infinite cn into delta of f minus n into f naught. This is an equation get of integral minus infinite to infinite of the exponential function. Understood, my dear students? Okay. The remaining part will continue in the next class, my dear students. So any doubts? So please raise. Thank you. Thank you, Anand.